All right, good. So welcome everyone. Today we'll talk about vectors, curves, and surfaces. So we will talk a little bit, we will go into the mathematics that we need for computer graphics. That reminds me, I think I forgot to mention last Tuesday to warn the mathematics students. I remember that I talked about that for this course we always have the strange situation that there are people with very different backgrounds, so people with no experience, people with a lot of experience, but I think I only talked about programming and graphics experience, but we also have a lot of mathematics students here who follow this course, and I realized that for them, the basic mathematics that we cover at the beginning of the lecture is usually very easy and very simple, so they get easily bored. And it actually happened a lot at the beginning that there were a lot of mathematics students who did great in the first exam, but horrible in the second exam because they kind of underestimated then the second part of the course when we talk more about the actual computer graphics stuff. And they kind of, hit the point where it would have been necessary for them to put more effort into the course. And then the problem appeared that I also warned you about, that it is a lot of material, and if you get lost, if you cannot catch up with the material, with the stuff, then you might end up before the exam not having enough time to learn everything. So for those of you for who this will be the case, just a warning. After I realized that, I always warn people about this, and that actually kind of helps. So the mathematics students are doing better now in this course, but there is always one or another where this happens, that the first exam is great and the second is horrible. So just as a warning. Good. So before we go into the mathematics, just a few practical and organizational announcements again. The tutorials are online now. The practicals I promised to put them online before the lecture. I didn't do that. I will put them online after the lecture. And the reason for that is that since we're doing the practicals completely new this year, I wanted to have someone to double check it before we put it online. So we said, okay, rather take 1 hour or 2 hours more to check it, and then I put it online directly after the lecture. So I will go to the tutorials after the lecture to see if everything works there, and then I will go to my office and put it online. So it should be online around 3:30 or 4, and then you can download them. Actually, I don't have a Blackboard here because you need a password for it, so I have to tell you this later. So the tutorials are already online, so you can download them, and the tutorials, the sessions with the teaching assistant start today. But the practicals, they don't start today. We decided to let them start next week because it doesn't make any sense to put the stuff online now and then let you immediately afterwards start working on it. So the idea both for the tutorials and for the practicals is basically you get an assignment in the practicals or an exercise sheet in the tutorials. And the idea is basically that you do the exercise and the assignments on your own or in small groups. In the practicals, you're actually required to do it in groups. But the time slots are there but then you have certain time slots where the teaching assistants are there to help you. I want to repeat that because I had the impression a couple of people didn't understand this last time and still asked me, in which group do I have to go or to which time slot do I have to go? We don't assign you to time slots because we expect that you do this stuff on your own. And the time slots is basically just an offer where teaching assistants are there to help you. So if you think you don't need any help, you're not required to go there. But if you think, for example, you need more help, then you're more than welcome to come to more than one session and ask the teaching assistants about it. But it's your initiative. So this is a university and you are at the end of your second year now, of your first year now at least. So you have to get a little more own initiative and not just do what people tell you. Because also, like, for example, the tutorial today, the exercise sheets, I'm pretty sure that most of you will not be able to finish that in 2 hours. But so we expect you to do a little more than just these 2-hour time slots, which is why we don't strictly assign them. So just go there. The only restriction we have is, of course, the space. So today we have 2 times 60 places for the tutorials. If you can't find a place today, go to the Tuesday tutorial. This covers the same exercise sheet. And as I said, it's basically you sit there and do the exercise yourself. So you don't have to, it doesn't matter on which day you do this. And the same is for the practicals. There, the space limitation is even more critical, of course, because we only have this one room, but the advantage is we have it the whole week. So if you get the practicals later today, you can have a look at them, and then if you think you don't need any help for it, which I think will be the case for a lot of you, because the first practical is basically just a tutorial that you have to do, where you go through all the steps to also set up the framework. It's also a little to help the people who don't have XNA or C# experience. And so you can also do this on your own. If you don't have a computer with XNA and Windows 7, you can go on Monday, for example, into the room. The room is open all the time. And I put a sign there that it's reserved for the graphics course. So if you see people there who are not from the graphics course and they take up your space and you need a place on a computer, you have the right to tell them to leave. And then on Tuesday, the tutorials start with the teaching assistant, the time slots with the teaching assistant start. So if you have a question or if you think you need help to get it done, then you can go to the Tuesday session or to the Wednesday or to the Thursday session. We schedule the session now that they are larger blocks, so it's more flexible for you. Because we have people here from the first and from the second year, so you all have different schedules. For example, I know that the first year students have on Thursday morning, most likely you all have the data structures course. So I recommend that the second year students focus more on Thursday morning and the first year students focus more on Tuesday or Wednesday. We will also be flexible with this. For example, if we see that no one shows up on Thursday before 11 o'clock, there's no point in having a teaching assistant there, then we might move this time slot to another day. Or if we see that one time slot is always very busy, we might say, okay, let's just have 7, but in one time slot have 2 people there. So we will see how it works out. If you at any time have the impression that you do not get the support from us that you need, if you would have time slots at different places, different times or anything, then let us know and we try our best to help you. You can also email the teaching assistants. I didn't put the email address of the teaching assistants online because the problem is then they get a lot of spam mail, but I put it on the sign that I put on the room. So if you go to BBL 175, the email addresses for the teaching assistants are listed there at the door. Good. And also the password, I will give it to you later because I don't have a Blackboard here, but the password that you need for the first assignment is also written there on the Blackboard, so you can also go there to check it. I will tell you later when the microphone is off. It's easy to remember. Yeah, it's a tutorial that we have. It's basically an online tutorial, but we made changes. We adapted it so it fits our local environment and the needs of the course. And because it's an online copyrighted tutorial, we cannot make it public. So that's why it's password protected. So don't distribute it or let people from the course, of course, let know the password, but no one else. Good. Let me see. Is there anything else? Yeah, team partners. You have to do it in teams of 2 or 3 students, the practicals. If you have problems finding a team partner, go to room 175 after the lecture on Tuesday and go to the teaching assistant. If everyone who hasn't have a team partner by then goes to a teaching assistant, it's easy to arrange it that everyone can join a team, and then you have your group to do the practical assignment. If it doesn't work out on Tuesday for whatever reasons, then come on Thursday after the lecture to the practice. I will tell the teaching assistants that they know about this and then they can try to arrange it. Good, so it should work out that way. All right. Good. Any organizational questions so far before we start? No? Good. Then let's start with the actual content. So just a quick refresh from last time. Last time I talked about, gave a high-level introduction to computer graphics. I said that The three major areas we're dealing with in computer graphics is modeling, rendering, and animation. And I also said we're not covering animation in this course. I also said we will only cover a little bit of modeling. So modeling is the process of describing a 3D virtual world that we want to put on the screen. And this process, exactly this, taking the 3D world onto the 2D screen, is then called rendering, and that means we have to project the 3D model on the 2D screen. If we follow a projective method, or we can't do ray tracing, but in any case we have to put a 3D world on a 2D screen, and not only the geometric representation of it, but of course also information such as color, structure, and how the material, how the objects look like, and this process is then called shading, and altogether it's called rendering. So as said, we have two basic methods for this. One is projection, where we have like a 3D world that we are modeling. So we have here our 3D world. For example, in this it's a very simple one where you just have a triangle, and then we have our 2D screen, and then we do a projection of this, and we define a position where our camera or our viewer is. So this is our user who sits in front of the computer, and this is either the computer screen, the whole computer screen, or a window on the screen where we want to put our graphic, and then we project the 3D world onto the 2D screen, and then we have to point, so we know which kind of pixels we have to color, and then we do the shading to get the information about what color to put into that pixel, and this process is then the projection. So we basically go from the projection to the observer, from the 3D world to the observer, whereas ray tracing takes the other way around. For ray tracing, we say, okay, we have an observer, and we're looking on the screen, and we're looking at one particular pixel, so we want to know what color we have to put into that pixel. So what we do for ray tracing is basically we go in the other direction, we look towards a pixel, and then we say, okay, this color that goes into that pixel must be the color of this. It's an annoying must be the color of the first object that I hit here when I follow this rail. So for example, it could be a sphere, but I do not only put the color from the sphere there, because how I see the color in a real life, or how I would see the color of this sphere at this particular position in real life, also depends, for example, on the light around it. So if I have a light source here, that influences it, but also how, something's wrong today. If like light is reflected onto this triangle and then reflected onto this sphere from the triangle, it also influences it. So what we do is we recursively from that point follow where the light comes from to get an idea about how we can put the optimum color on this point here, or on this pixel actually on the screen. So we go recursively, and we will we'll talk about how to do this in detail at the end of the lecture, and we'll talk about ray tracing. So we go recursively through the objects, and this is why ray tracing takes very long, because we have to recursively consider the objects, and in theory every object that is there in our virtual world can have an influence on the color of a particular object, because the light can reflect from everywhere. This is why it takes very long, but this is also why ray tracing produces very realistic images and very good results, because it considers all the lighting conditions that you have in a room, whereas projective methods usually make some sort of simplification because it would be too difficult to calculate them. But because of these simplifications, of course, it goes faster. So in general, projective methods are usually faster than ray tracing, but they are not as good in the quality as ray tracing, although we also already have very, very good projective methods that produce very high quality results, as you probably know. So in reality, and we also have approaches on like making ray tracing faster. Real-time ray tracing is an interesting research area, so this is coming more and more together. Good, so we will start in the lecture with the projective methods, and then at the end we will talk a little bit about ray tracing. So, and for the projective methods, I said that this process of taking the 3D world and transforming it into objects, into pixels on the screen, is called the graphics pipeline. So it's basically a description of the single steps involved. And you see here, last time I already used the term pixel without really introducing it. And of course, I think most of you know what a pixel is. But of course, when we want to do it in graphics, we have to be a little specific and think about what it really means. So in graphics, we usually deal deal, or most of the time we're talking, when I say bringing something onto the screen, I mean about a raster display. A raster display is basically just a rectangular area of single points or pixel. So pixel is short for picture element. It's basically the smallest unit you have on a screen, or informally said, it's basically a single dot that makes up, it's all those single dots that together make up your final image. So you know that when you look on the screen, when you go very close, then usually you see that the image are single dots. But if you go further away, you cannot realize the dots anymore because you're too far away, and then it becomes the reality if you're seeing a real image there. Good. I'm not going to cover the raster image and the pixel related color stuff in this course here. If you're interested in that, you can read the 3rd chapter from the book. But as I said, it's not required, so this is not covered in the course. But just if you're interested, then read it. What you need to know is about this is I'm going to tell this here in the lecture. And you probably remember from last time that this process of going from the 2D geometry that we projected to the actual pixels that we color, that we called this project rasterization. So what we do is we project the 3D object on a 2D screen, but then we still have a geometry. So we have a 2D geometry or geometric description in 2D of our image. So you see here, for example, this triangle is described by 3 points. And then, of course, we also have information about the color and how it looks like, the material, which we then use in the rastering process, where we then basically just have pixels on the screen. And then we have to decide, first of all, which pixel of the screen belong to the triangle and which pixel, what kind of color do we give to each pixel. And so the reason why we do this with the geometry and the pixel is, of course, the geometry is easier to calculate, easier to modify. We don't, like if Pixar does a movie, they don't go to each single frame and then draw each individual pixel, but they calculate the models and then do the calculation. And we cannot do the calculation based on pixel level, but we have to do it with a certain geometry. And the other thing is, of course, by doing it with the geometry, you become independent of the hardware, because when you draw the pixel on the screen, you have to, of course, consider the hardware. So, for example, if you have a graphic and display it on a large screen or displayed on a small screen, you have a different amount of pixels. So you have to, when you do the rasterization, you have to consider the hardware, for example, the screen resolution. So this image is actually a little confusing. You could also have, like here, a much smaller raster image or a much larger one that goes on here. And then in each case, you can display the triangle here, and then of course it gets a different size. Good. So so we will cover this rasterization step later in the lecture, but let's just have a quick look at this last step, because that is actually a good transition to the geometry part, which we'll cover today. So the goal is to put a 2D geometry on the screen or on the pixel. So to do this process is called windowing transformation. So this is basically from the 2D geometry to the 1D screen. And if we have the 2D geometry and then we have the screen, and they are both rectangular, then it's basically just a scaling. So you have an exercise in the tutorial that goes into that, and that where you basically have to figure out how this works. But yeah, it's basically just a scaling. I mean, you can imagine that if you have a width in your geometry, in your rectangle, and then you have to map it to a certain screen, what you need to know is you need to know how big the screen or the window where you want to draw your graphic is. You need to know how high it is. You need to know the left and 2 corners of the rectangle to define it. And then you need some sort of index so you can address a single X pixel within that index. And we usually do this by using the row with the letter I and the column with the letter J. So we have a pair of I and J that describes each individual pixel on this raster image. Good. And so this is basically just the scaling. And as I said, you will do this in the tutorials, hopefully. And the interesting thing here when we go to the geometry is, of course, that this kind of how this uniquely describes the pixels on the screen. So it uniquely describes the pixels on the screen, but this is also a method to uniquely describe the pixels in the 2D geometry, because if we have a 2D geometry, we need to define points, for example, to define a triangle, so we need to be able to uniquely describe them. And what we use is so-called vectors. Probably some of you have already heard that in other math classes. The vectors are basically a generalization of this pixel pair that I have here, a generalization first in terms of the space. So if we look at the geometry in our 3D world, or the projection, the 2D projection of it, we're not limited to a screen display, but we have a whole plane where we can display our virtual world. So we're generalizing in both directions, and also a generalization when we go to 3D, because then we basically have a plane in front of it, or we have an infinite number of planes after each other, and that way, by adding a third index, we can uniquely describe each point in this three-dimensional space that we have here. And you actually already see here that here we have already a third value here, which is 0, because in this case on the screen we only have 2 dimensions, so the third dimension is just set to 0. But if you allow this third dimension, and you can imagine that you have an infinite possibility of addressing each point in a 3D space. And this is basically what vectors do. So a vector can be defined just as an ordered d-tuple because of the dimension. So in 2D we have 2 dimensions, which, as you saw in the array, if you think about an infinite array, but as long as you have a reference point like an origin, so for example, if we say here that this is 0, 0, 0, then we can address each point here by the row index and the column index, and with reference to this 0, 0, 0. And of course we can do this also in 3 dimensions. We define an origin somewhere, which is 0, 0, 0, and then we can address from that origin all points in our 3-dimensional space, which is basically a 3-dimensional array. Good. We can also define a vector in a different way, by using a more geometric interpretation of it, and this is the definition of a vector by its length and its direction. And this can of course be easily seen in 2D and in 3D, that we say a vector is basically an arrow that points somewhere, so it has a direction and it also has a length. And so this is just another way to define it, and these are both valid definitions for the very same thing. But for example, if you look at the second one, you kind of see that this is kind of independent of a location, whereas in the first case you have concrete numbers, but a length and a direction doesn't give you any indication about location. So for example, if I draw a vector here, from here to here, yeah, so this should, no, this is not a vector. So from here to here, this, if it would be a straight line, it would be exactly the same, have the same length and the same direction as the other red vector here. So it is per definition the very same vector, but if you look at the numbers, you would say, well, but these are different numbers. But if you look at it, how these numbers are in our grid system that we have here, then you also have here 5, like you have here 5, and you also have 1 here, like here. So it is actually also in terms of the number the very same vector. So vectors are independent of location. So this is a very important characteristic, and also a very confusing characteristic sometimes, because vectors are usually used, especially in graphics, to describe a location, but per default a vector is something different than a location. So you can think about it, maybe a good metaphor for this is when you think about driving. If I say I drive 50 kilometers west or northeast, that gives you a direction and it gives you a distance, but it doesn't really say anything about a location. You can relate it to a location, because if I'm standing here and I say I go like 10 meters in that direction, that gives you a concrete location, but it is the pure description of it does not contain any information about the location. So and that is what a vector is. A vector describes a direction and a position, but it can be used to describe a position, but per default the vector does not have a location or a position. So if you call me on my phone and I tell you, and you ask what are you doing, and I say I'm going 20 meters northeast now, you have no idea where I am or where I'm going, because what I'm describing you is like a vector. Good. Of course, we can also use locations to describe, to define a vector, because if I'm standing here and I'm going over there, then I'm also giving you implicitly a vector, because I'm implicitly giving you a distance and a location and a direction. But it is, and in a lot of situations, it just, from the context, it's clear what you mean if you mean a vector or a location, or it's sometimes not even necessary to make the distinction. But there are situations in graphics where it is important to make a distinction between it. For example, when we calculate with it, because we want to use vectors to, for example, describe objects or to manipulate objects. So if I say these 3 points here in my space are defined by a triangle, and if I move the triangle, of course, I can do this by manipulating the vectors that represent the current location of my triangle, but I can only modify the vectors, the vectors indicating the location of the triangle, but I will not change the actual location in my space. And right now it might seem very picky that I'm making this distinction, but we will see later in this course that when we do the calculation, we actually really have to be careful that we make this distinction. Good. So yeah, this is just some words on the notation. There are different ways to notate vectors. So a very common way that you already saw in the example is here as a column. And if you have, for example, 3 dimensions, then you need, of course, 3 coefficients to describe your position in the 3D space. And then you sometimes call them, if you have a vector v, you call them v1, v2, v3, or sometimes we name those positions with x, y, and z, and then we name the coefficients of the vector with vx, vy, vz, or x, y, z for the vector v. We also could write them in a line with commas to save some space. It's sometimes more convenient. Or we can write them, if we write them without commas, we have to make a T here. The T stands for transposed. So this is just the notation, just to let you know, depending on where you look in the book or in other books or in the practicals, you will see different notations, but they usually mean the same. Also, there exist different symbols to notate a vector. So for example, in the book, they use boldface. I often use this arrow on top. Actually not consistently. I forgot to update the images. Sorry for that. So sometimes also the same is used here. So this is bad. Don't do that. So I don't mind what you do, but just be consistent and be careful in the exam if you write it in a way that we are not sure if it really means a vector or just a single number, then you might get deduction of your credit for that. So just be consistent and be careful that it's always clear that you mean that people understand what you mean if you talk about a vector or just a number. Good. Yeah, so I basically already said something about this now when I talked about this difference between a vector and a location. So there are different interpretations of what a vector is. The algebraic information is that the Cartesian coordinate system is something I will talk about later. So don't worry if you don't know what it is right now. But if you have like a coordinate system or like the grid that I used at the beginning to introduce this, then you can see this basically just as a vector represents a point. But remember, a vector is not a point, it's not a location, it's just a way to represent a location. And that becomes much clearer if we look at the geometric interpretation, where we see a vector basically just as an arrow, which has of course an offset. So if we just have the numbers here, we can say, okay, this is the offset from the offset is from the origin, and then we go 5 in that direction and 1 in that direction, and we get this arrow. But if we are put the offset here, then of course also going 5 in that direction and 1 in that direction gives us the very same arrow. So it's basically an arrow that is invariant towards translation, so you can put it anywhere and can use it, for example, not only to describe this position with respect to the origin, but you can also use it to describe this position. So for example, if we have a triangle here, you can use this vector to describe a translation of this triangle from this position to this position by moving all the 3 points with the same vector. Good. Yeah, it looks horrible, I know, but yeah, I hope you understand what I mean. You have to draw better in the exam because you don't have a tablet. It's not that easy with this thing here. But I think it's I had have the impression that it helps a lot of people if I do not just put the slides there and talk about them, if I do a little bit also with the handwriting. Good. So we said that we can use the direction and the length to define a vector, but we also said we can use numbers to define a vector or an n-tuple to define a vector. But then, of course, the interesting question is if those two definitions are equivalent, how can we go from one to another? For example, how can we get the length of a vector when we just have the number? And we can use this formula to get this, and you can see why this actually gives the length of a vector. You can see this easily from 2D. So probably from school you are familiar with this Pythagoras theorem, which says that if you have a triangle with a right angle here and 3 sides A, B, and C, then the length of the side on the other side of the side of the triangle that is on the opposite side of the right angle is to the square is the same as a to the power of 2 plus b to the power of 2. Now, if you think about a vector v with an x value here and a y value here, then this side here is of course the length of this vector. This is a right angle, and I'm pretty sure you are able now to make the connection between this and this here, and you see why at least in 3D this in 2D this is really the length of this vector. And of course we can generalize this to random dimension. Of course, for us the 3-dimension are the most interesting, but I often draw in 2D because it's easier to draw in 2D, of course. Good. Yeah, so now we know how to describe vectors, but we also want to do something with them. Of course, we want to use them to describe objects, for example. So one of the things we can do is so-called scalar multiplication, and that is just a way to manipulate the length of a vector by multiplying them with a scalar value. So a scalar is basically just a single number in contrast to a vector, which is a collection of numbers. And again, you can think about this driving example. If I tell you I drive 50 miles per hour, that's just a single number. There is no direction and no length to it associated. It's just a single number that doesn't give you any other information. But if I say, for example, I drive in that direction for 10 minutes at 50 miles per hour, you know how far I get. If I say I drive now with 20 miles per hour, you know I'm getting a little less far. If I say I drive 100 miles an hour, I get twice as far. And this is basically also what scalar multiplication does with vectors. If you multiply a scalar to a vector in a way that you take the scalar value and multiply it with each single coefficient of the vector, you basically change the length of the vector. So the direction stays the same, but you just make the vector larger or shorter, depending if lambda is larger or smaller than 1. And if it is larger than 0, of course, then lambda is larger 0, then you go in the same direction. If lambda is smaller than 0, then you go in the other direction, but you're not changing the direction, you're changing it in terms of front and back, but you're not changing it in another way. And of course, if lambda is 0, then the result of your vector is a vector with all zeros, and this is such a special vector that we give it a special name. We call this the null vector. Good. All right, so we know now when we multiply a vector with a scalar, we cannot change its direction except for plus and minus, but so the resulting vector has a different length, but they are all kind of similar, kind of related, because they're all pointing in the same direction or directly in the opposite direction. And this is why they form a certain group, and we call them parallel. So a vector that can be created by from another vector by multiplying it with a scalar is called a parallel vector. You probably know from school. In school you often say two lines are parallel if they don't intersect with each other. For vectors, you kind of get the idea that if a vector is created by multiplying it with a scalar, it just gets longer. So it is either identical with it or it is next to it, but you cannot, by multiplying it, make it that two vectors overlap each other or intersect each other in one point. Good. Yeah. And for the null vector, of course, because the null vector doesn't really have a direction, it is usually considered neither parallel nor non-parallel, because for the null vector, of course, that would always be the case. If you put lambda to 0, then you always get a null vector. Good, so this is just a convention. Another interesting vector that is very important is the unit vector. That is the vector that has the length 1. And we can create that with, or very often in graphics is... Yeah, you have a question. There is only one null vector. There is only one null vector. Because the vector terminology is something that uniquely defines a point in a certain space. So if you have a 3D space, then the vector 0, 0, 0 uniquely defines one position in that space. So a second vector would be exactly the same. Good. Yeah. But it's good that you ask these kind of things, because a lot of these things sound very simple and straightforward, which is what I meant, that a lot of people at the beginning sometimes get bored here. But it is important that you get a feeling for this and that you have an intuitive understanding of it, because then later you will do much more complex processing with it, and if you lack this intuitive understanding of it, you will have a much harder time doing it. Good. So the other important vector is the unit vector, and in graphics sometimes you will see that it's very convenient to have a vector of a length 1, because we're just interested in the direction but not in the length, and if we have a 1, it's easier to calculate with. But for example, if you do a multiplication with 1, the result is always very easy to get. So an interesting question is, how can we get, if we have an arbitrary vector, how can we create a unit vector that points in exactly the same direction? I'm running a little bit out of time, so I will do this myself and not ask you. The idea is basically, if you think about it, if we have, for example, this vector. Oh, no, let's draw here. It's easier. Let's say we have this vector and want to have a vector that goes also in the same direction, but just has the length 1. How can we do that? Well, we just, yeah. Exactly. We divide the components by the length of the vector. And you can easily make this clear to yourself by thinking about what we said about scalar multiplication. So we don't want to change the direction, we just want to change the length. So we have to multiply it with something. The question is, what is this something? And as you really said, already said correctly, it's the length, and you can intuitively make this clear to yourself. If you have a length of, I don't know, 23, 72, and you want to put that down to 1, you divide it by the same value. If you divide 23 divided by 23, it's 1. If you divide 72 by 72, it's 1. So we divide it by the length, and then we get a length of 1. Of course, this is the intuitive way how you can come up with the solution, but you can also prove this you can also prove this, of course, for example. You can also prove this. So if you want to have the unit vector, it is the vector multiplied with 1 divided by the length of this vector. So it's basically a scalar multiplication, which in that case means dividing each coordinate by its length. And you can prove that, and you will do that in the tutorials. Good. Now, okay, the other question, can every vector be normalized? Yeah, exactly. Every vector besides the null vector. Good, because the null vector per definition doesn't have a length, so it also doesn't make any sense, or it does have a direction. So how would you create a vector of the length 1 in which direction? So it doesn't make sense from from a geometric point of view, but it also doesn't make sense, or it's not allowed in terms of the arithmetic behind it, because you're not allowed to divide by 0. Good. So so now with the scalar multiplication, we can change the length of a vector, but we cannot change the direction. But of course, if we want to use vectors to describe objects in our world, we need to be able to create vectors that point in a random direction. And one of the ways to do this is to use vectors to create other vectors by adding them. And we define the addition of two vectors by just adding the single coefficients of each vector. So if we have a vector v and w, we add the first coordinate. To have a new first coordinate, we take the second coordinate, add it, and get the second one. And you see this here in this image, and this also kind of reminds you that vectors are not locations. So vectors are just indications of a direction and a length. So if we have, for example, a vector here and a vector here, we can take that vector and add it to that vector by, for example, taking it and connecting it to the end here. And then we end up by this vector here. And when you compare it to this here, you will see that this is exactly the same as we defined here from the arithmetic, that this is the same that we would intuitively say from the image. From the image, we also see that there is not much of a difference if we take this vector and connect it here, or if we say we leave this vector here and then add this vector to this end here. In both cases, we end up at the same position, which means that the addition of vectors is commutative. So that means if I take a vector v and add it with a vector w, I get the same result as if I take the vector w and add the vector v. And of course, this is intuitively clear from the image. This is from the image. It's sometimes also called the parallelogram rule. Yeah, you know what I mean. And but of course, you can also show this algebraically. And so what you basically do here is you write this down in this general form here. And then you write it for v plus w, and then you write the same for w plus v, and then you see that they are identical. Sometimes you have to make some small variations of it. So this is why this is, I will not do this here, this is an exercise. I'm not sure if it is on the tutorial, so maybe it's a home exercise. Good. So we have addition. Of course, we also can think about subtraction. How can we define subtraction from what we already have? It's actually pretty easy to define. Any idea? Yeah. Sorry. Inverse, exactly. Yeah. Exactly. So we inverse one vector, and with what we defined already, we can just say it's a scalar multiplication with -1, and that results in the reverse vector. So if we say v is v plus lambda w, and lambda is -1, we have our subtraction, and that is exactly the inverse of the vector. So if we inverse this vector and add it here, we get minus. Good. Yeah. So let's make a break here. Good. So we continue in 50 minutes.